Space, an unexplored mystery filled with the answers we have yet to see. It is the ultimate frontier, not just of exploration, but of our quest for understanding, meaning, and our place within the cosmos. As we stand on the precipice of the known, gazing into the vast expanse that stretches beyond our comprehension, we embark on a journey that is as much about discovering the universe as it is about discovering ourselves. The observable universe, with its billions of galaxies, each teeming with stars and planets, is a testament to the complexity and majesty of nature. In this documentary, we will traverse the cosmic distances, not just to chart the stars and their secrets, but to explore the profound questions that have captivated humanity since we first looked up at the night sky. What lies at the very edge of our observable universe? Are we alone in the universe, or is it teeming with life, awaiting to be found? The universe, a vast expanse stretching beyond the farthest reaches of human imagination, encompasses all of space, time, matter, and energy. At its heart, the universe is a tapestry woven from the threads of galaxies, stars, planets, and the very fabric of space-time itself. Scientists estimate its age at approximately 13.8 billion years, a figure derived from measuring the motion of galaxies and the cosmic microwave background radiation, the afterglow of the Big Bang. This monumental event marks the inception of the universe, from an infinitely dense point known as a singularity, expanding and evolving into the cosmos we observe today. One of the most intriguing aspects of the universe is its composition. It consists of only about 5% ordinary matter, the stars, planets, and galaxies visible to us. The rest is dark matter and dark energy, mysterious entities that do not emit light or energy but exert a profound influence on the universe's structure and expansion. Dark matter, making up about 27%, acts as the cosmic glue holding galaxies together, while dark energy, accounting for roughly 68%, drives the universe's accelerated expansion, a discovery that has reshaped our understanding of cosmology and led to a Nobel Prize in Physics in 2011. Understanding the universe also invites us to ponder the fundamental nature of reality and our place within it, intertwining cosmology with philosophy. Philosophers and scientists alike delve into questions about the universe's origin, its ultimate fate, and the laws governing its behavior. This quest for knowledge challenges our perceptions, pushing us to consider not just the mechanics of celestial bodies, but the very essence of existence itself. It beckons us to explore concepts such as the multiverse theory, suggesting that our universe might be just one of countless others, each with its own unique laws and constants. The quest to determine the age of the universe is a story woven through centuries of astronomical observations and theoretical breakthroughs. This journey traces back to the earliest civilizations, where humans first looked up at the stars and pondered their origins. However, the scientific pursuit of the universe's age began to take shape in the 20th century, following significant discoveries in physics and astronomy. The turning point came with Edwin Hubble's observation in 1929 that galaxies are moving away from us, suggesting that the universe is expanding. This discovery laid the groundwork for the Big Bang theory, the leading explanation for the origin of the universe. By measuring the speed at which galaxies recede from us, astronomers could infer the rate of expansion of the universe, known as the Hubble constant. Initial estimates of this constant suggested a younger universe, but as measurements became more precise, the age was revised upwards. In the late 20th and early 21st centuries, the advent of more sophisticated technology, such as the Hubble Space Telescope and later the Planck satellite, refined our understanding of the cosmic microwave background radiation. These observations provided a clearer picture of the universe's early moments and helped narrow down the Hubble constant to a more accurate value. The Planck satellite data, released in the 2010 S, played a pivotal role in this, measuring the cosmic microwave background with unprecedented precision and leading to the current estimate of the universe's age at about 13.8 billion years. The determination of the universe's age also relies on understanding the life cycles of stars. By observing the oldest stars within globular clusters, which are dense groups of stars held together by gravity, astronomers can infer the minimum age of the universe. These stars, some of the first to form after the Big Bang, offer a stellar clock by which to gauge cosmic history. The oldest of these stars are found to be nearly as old as the universe itself, around 13 billion years, providing a lower limit to the age of the cosmos. As we delve further into the mysteries of the cosmos, the concept of the observable universe emerges as a fascinating topic that builds upon our understanding of the universe's vastness and age. The observable universe refers to the portion of the entire universe that we can see or detect from Earth, limited by the speed of light and the age of the universe. Since light travels at a finite speed, approximately 299,792 kilometers per second, it takes time for light from distant objects to reach us. Therefore, the observable universe is essentially a sphere with Earth at its center, extending outwards to a radius of about 46.5 billion light-years. This radius marks the furthest distance from which light has had enough time to travel to us since the beginning of the universe approximately 13.8 billion years ago. The distinction between the observable universe and the entire universe is crucial. While the former is the part we can see, the latter encompasses all of space, much of which remains beyond our current observational capabilities. The size of the entire universe remains unknown and may be infinitely large or wrapped back onto itself in a way that defies our standard notions of geometry. The observable universe contains an estimated 2 trillion galaxies, each harboring millions to trillions of stars, along with an even greater number of planets, asteroids, and comets. This staggering number comes from deep sky surveys and observations made by telescopes like the Hubble Space Telescope, which have peered back in time to glimpse the universe as it was shortly after its birth. These observations have not only expanded our knowledge of the cosmos's scale, but have also provided insights into the formation and evolution of cosmic structures. Understanding the observable universe also involves grappling with concepts such as cosmic inflation, a theory suggesting that the universe underwent an exponential expansion in its first fractions of a second. This rapid expansion stretched the fabric of space itself, leading to the vast distances between galaxies we observe today. It's a concept that bridges the gap between cosmology and theoretical physics, offering explanations for the uniformity of the cosmic microwave background radiation and the distribution of galaxies across the sky. In exploring the observable universe, we're confronted with the limitations of our current technology and the laws of physics. The light from objects beyond the observable universe has not yet had time to reach us, rendering these regions beyond our current sight. Yet, advancements in telescope technology and observational techniques continue to push the boundaries of what we can see, unveiling more about the universe's structure, history, and the fundamental laws that govern it. So, how do we observe this vast cosmos, stretching billions of light-years across? Observing the universe is a multifaceted endeavor that employs a variety of technologies and methodologies, each designed to capture different aspects of cosmic phenomena. At the heart of this exploration are telescopes, instruments that have been refined over centuries, from Galileo's simple optical telescopes to today's sophisticated observatories that can detect a range of electromagnetic radiation beyond just visible light, including radio waves, infrared, ultraviolet, X-rays, and gamma rays. Optical telescopes, which collect visible light, have been instrumental in our initial forays into space observation. They allow us to see stars, galaxies, and nebulae within the observable universe. However, To understand the universe's full complexity, we've had to go beyond the visible spectrum. Radio telescopes, for example, can detect radio waves emitted by distant cosmic objects. These instruments have unveiled phenomena invisible to optical telescopes, such as the cosmic microwave background radiation, a relic from the universe's infancy, providing crucial evidence for the Big Bang theory. Infrared astronomy opens a window to observe celestial objects hidden by dust clouds that visible light cannot penetrate. It has revealed new stars in the process of formation and galaxies in the distant universe, obscured from view in the visible spectrum. Similarly, X-ray and gamma-ray astronomy allow us to study high-energy processes, such as those occurring around black holes and neutron stars, offering insights into the most violent and energetic events in the cosmos. The advancement of space-based telescopes has marked a significant leap in our observational capabilities. Instruments like the Hubble Space Telescope, orbiting outside Earth's atmosphere, provide clearer and more detailed images free from atmospheric distortion. The James Webb Space Telescope, launched to succeed Hubble, focuses on infrared astronomy, aiming to observe the universe's first galaxies and delve deeper into the mysteries of star and planet formation. Observing the universe also extends beyond electromagnetic radiation. Neutrino observatories detect nearly massless particles that offer clues about solar processes and supernovae. Gravitational wave observatories, such as LIGO, Laser Interferometer Gravitational Wave Observatory, have opened a new avenue of exploration by detecting ripples in the fabric of space-time itself, generated by cataclysmic events like the collision of black holes or neutron stars. This method provides a unique perspective on the universe, enabling us to study phenomena that emit little to no light. The process of observing the universe is an ever-evolving field, driven by technological innovation and theoretical advancements. Delving deeper into our cosmic journey, we encounter a natural curiosity about the limits of our observation. Why can't we see beyond the observable universe? This question touches on fundamental aspects of physics and the nature of the universe itself. The observable universe is defined by the farthest reaches from which light has had time to travel to us since the universe's inception, about 13.8 billion years ago. This boundary is not a physical one, but a limitation imposed by the finite speed of light and the age of the universe. Light travels at a constant speed of about 299,792 kilometers per second in a vacuum. This speed sets a cosmic speed limit, dictating how far we can see into the universe. Since the universe is about 13.8 billion years old, the farthest light we can observe has traveled from a distance that corresponds to the universe's age, allowing us to see as far back as the cosmic light horizon. This horizon marks the edge of the observable universe, about 46.5 billion light-years away due to the universe's expansion since the Big Bang. Beyond this horizon lies the unobservable universe, which remains hidden from our view because the light from these regions has not yet had enough time to reach us. Furthermore, the expansion of the universe, driven by dark energy, causes distant galaxies to recede from us at speeds that increase with distance. At a certain point, known as the Hubble length, this recession speed exceeds the speed of light. This doesn't violate Einstein's theory of relativity, which prohibits objects within space from moving faster than light, because it's the fabric of space itself that is expanding. The concept of the observable universe also ties into the theory of cosmic inflation, which posits that the universe underwent an exponential expansion in the first fractions of a second after the Big Bang. This rapid expansion stretched the fabric of space, moving some regions so far away that their light will never reach us, further limiting our view. This boundary of visibility isn't just about distance. It's also about time. Looking out into the universe is akin to looking back in time. The further we look, the older the light, until we reach the cosmic microwave background radiation, the afterglow of the Big Bang, which represents the earliest light that can be observed. Beyond this backdrop lies the era of the universe that predates starlight, a period known as the Cosmic Dark Ages. As we venture further into the cosmos, seeking to unveil the mysteries that lie beyond our immediate perception, astronomers employ an arsenal of sophisticated tools to observe distant objects. These instruments, each designed to capture different aspects of the universe, allow us to peer into the depths of space and time, revealing the cosmos in unprecedented detail. At the forefront of these observational tools are telescopes, which come in various forms tailored to different wavelengths of light. Optical telescopes, which collect visible light, have been the backbone of astronomy for centuries. These instruments, ranging from ground-based observatories to space telescopes like the Hubble Space Telescope, enable us to observe planets, stars, galaxies, and nebulae in the visible spectrum. However, the universe emits information across a broad spectrum of light, much of which is invisible to the naked eye. To capture this information, astronomers utilize radio telescopes to detect radio waves from space. These telescopes, such as the Very Large Array in New Mexico or the Atacama Large Millimeter Submillimeter Array in Chile, can observe the cold, dark regions of the universe, such as gas and dust clouds where new stars are born, or the remnants of the Big Bang itself. Infrared telescopes like the Spitzer Space Telescope pierce through cosmic dust clouds to reveal hidden star clusters and galaxies, providing insights into star formation and the early universe. Conversely, X-ray and gamma-ray observatories, including the Chandra X-ray Observatory and the Fermi Gamma Ray Space Telescope, explore the universe's most energetic phenomena, such as black holes, neutron stars, and supernovae, uncovering the mechanisms behind these powerful events. Beyond electromagnetic radiation, recent advancements have introduced new tools for astronomical observation. Gravitational wave detectors such as LIGO and Virgo have opened a new window onto the cosmos by capturing ripples in the fabric of space-time produced by cataclysmic events like the mergers of black holes or neutron stars. This breakthrough has inaugurated the era of multi-messenger astronomy, where gravitational waves and electromagnetic signals are combined to provide a more complete picture of cosmic events. Neutrino observatories, like the IceCube Neutrino Observatory located in the Antarctic ice, detect nearly massless particles that traverse space unimpeded, offering a unique perspective on astrophysical processes such as solar fusion and supernova explosions. The pursuit of understanding distant objects in the universe is also propelled by interplanetary missions. Spacecraft and probes like the Voyager probes, the New Horizons mission to Pluto, and the Mars rovers extend our sensory reach, providing up-close observations of planets, moons, and other celestial bodies within our solar system and beyond. Each of these tools plays a critical role in unraveling the mysteries of the cosmos. By combining observations across the electromagnetic spectrum with the new vistas opened by gravitational waves and neutrinos, astronomers can construct a more comprehensive understanding of the universe's structure, evolution, and the fundamental laws that govern it. Our understanding of the universe has undergone profound transformations over the centuries, evolving from ancient cosmologies to the sophisticated, data-driven view of the cosmos we hold today. This journey of discovery reflects humanity's enduring quest to comprehend the vastness of space and our place within it. In ancient times, civilizations across the world conceived of the universe in terms that blended mythology with early astronomical observations. The Greeks, for example, saw the heavens as a crystal sphere encapsulating the Earth, with stars fixed upon this sphere. This geocentric model, placing Earth at the center of the universe, dominated Western thought until the Renaissance. The 16th and 17th centuries marked a pivotal shift with the work of Nicholas Copernicus, who proposed a heliocentric model, placing the Sun, not the Earth, at the center of the universe. This idea, revolutionary at the time, laid the groundwork for further breakthroughs. Johannes Kepler and Galileo Galilei, through meticulous observations and mathematical laws, provided strong evidence for heliocentrism, challenging centuries-old beliefs and setting the stage for modern astronomy. The invention of the telescope in the early 17th century allowed Galileo to make groundbreaking observations, such as the moons of Jupiter and the phases of Venus, that further discredited the geocentric model. This period marked the beginning of a transition from a philosophy-based understanding of the cosmos to one grounded in empirical evidence and observation. As telescopic technology advanced, so too did our understanding of the universe. The 18th and 19th centuries saw the discovery of new planets within our solar system, and the 20th century brought the realization that galaxies extend far beyond the Milky Way, with Edwin Hubble providing evidence of an expanding universe. This discovery supported the Big Bang theory, suggesting that the universe had a definite beginning. In the latter half of the 20th century and into the 21st, our view of the universe has expanded dramatically with the launch of space telescopes and the development of advanced ground-based observatories. These tools have allowed astronomers to detect exoplanets orbiting distant stars, observe the cosmic microwave background radiation, a relic of the Big Bang, and map the distribution of dark matter and dark energy, which constitute the majority of the universe's mass energy content. Today, our understanding of the universe is framed by the Lambda CDM model, which describes a cosmos dominated by dark energy and dark matter, with the ordinary matter that makes up stars, planets, and life forms playing a relatively minor role. This model, supported by observations from instruments like the Hubble Space Telescope and the Large Hadron Collider, presents a universe that is 13.8 billion years old, constantly expanding and filled with a web of galaxies that stretch across vast cosmic distances. The evolution of our understanding of the universe is a testament to human curiosity and the relentless pursuit of knowledge. It's a narrative that has shifted from Earth-centric models to a vast, expanding cosmos where Earth is but a tiny speck in an immense universe. In the realm of cosmic exploration, the term light year plays a crucial role in bridging the vast distances that separate celestial bodies. A light year is not a measure of time, as one might initially think, but rather a measure of distance. It defines the length that light, traveling at a constant speed of about 299,792 kilometers per second in the vacuum of space, covers in one Earth year. This distance amounts to approximately 9.46 trillion kilometers, or about 5.88 trillion miles. Given the immense scales involved when discussing the universe, using light years to measure distances allows astronomers and cosmologists to convey the vast expanses between stars, galaxies, and other cosmic phenomena in a more comprehensible manner. The adoption of the light year as a unit of distance is pivotal for several reasons. Firstly, it provides a standardized metric that encapsulates the immense scales of the universe in terms understandable to human cognition. When we say a star is 4.37 light-years away, as is the case with Proxima Centauri, the nearest known star to the Sun, we immediately grasp that its light, the light we see today, embarked on its journey to Earth 4.37 years ago. This time, encapsulation within distance measurement offers a direct connection between the concept of time and the vastness of space, emphasizing the universe's dynamic nature. Moreover, Employing light years as a unit of measurement aligns with the fundamental principles of physics and astronomy. Since the speed of light is a constant, a cornerstone of Albert Einstein's theory of relativity, it provides a stable basis for measuring cosmic distances. This constancy ensures that the light year is a universal measure, applicable and relevant across different observational and theoretical contexts in astrophysics and cosmology. The use of light years also facilitates communication and understanding across the scientific community and the public. When astronomers discover a new galaxy 100 million light-years away, it instantaneously imparts a sense of the incredible distances and timescales involved in the cosmos. It helps illustrate not just the spatial relationships between cosmic objects, but also their temporal relationships, as looking out into space is simultaneously a journey back in time due to the time it takes for light to travel these immense distances. The formation and evolution of galaxies are fundamental processes that reveal the universe's dynamic nature, unfolding over billions of years. This narrative begins shortly after the Big Bang, the explosive event that marked the birth of the universe approximately 13.8 billion years ago. In the aftermath of this cosmic inception, the universe was a hot, dense plasma of particles and radiation. As it expanded and cooled, matter began to coalesce under the force of gravity, setting the stage for the formation of galaxies. The earliest galaxies began to take shape from small fluctuations in the density of the universe's primordial matter. These overdensities, tiny ripples in the fabric of the cosmos, amplified by the gravitational pull of dark matter, attracted baryonic, ordinary matter. Gas clouds within these dark matter halos cooled and collapsed, fragmenting into smaller clumps where the conditions were ripe for star formation. This process led to the birth of the first stars and proto-galaxies, mere hundreds of millions of years after the Big Bang, during an era known as the Cosmic Dawn. Galaxies evolve through a variety of mechanisms. One primary driver is the process of star formation. Within galaxies, dense regions of gas and dust collapse under their own gravity, igniting nuclear fusion in their cores and giving birth to new stars. The life cycles of these stars, from their fiery births to their explosive deaths as supernovae, inject energy and heavy elements back into the galaxy, fueling further star formation and contributing to the galaxy's chemical enrichment. Another key mechanism in galactic evolution is the merger of galaxies. Gravity pulls galaxies towards each other, leading to collisions and mergers that can dramatically alter their structures. These cosmic encounters can spur bursts of star formation, reshape spiral galaxies into elliptical ones, and grow supermassive black holes at their centers. The Milky Way itself is on a collision course with the Andromeda Galaxy, with the two expected to merge in about 4 billion years, a testament to the ever-changing nature of galaxies. Throughout their lives, galaxies undergo various transformations, influenced by their environments and interactions. Some may collide and merge, others may strip gas from their neighbors, and many evolve in isolation, slowly converting their gas into stars over time. The rate of star formation and the influence of central black holes, which can both trigger and suppress the formation of stars, play crucial roles in determining a galaxy's appearance and fate. The study of galaxy formation and evolution is a vibrant field of research, leveraging observations from telescopes across the electromagnetic spectrum and simulations on powerful computers. These studies aim to piece together the complex story of galaxies, from their earliest origins in the smooth, uniform universe of the Big Bang to the intricate, diverse structures we observe today. Within our universe, so-called superclusters represent some of the largest and most awe-inspiring structures, embodying the immense scale and complexity of the cosmos. These colossal formations consist of groups of galaxies and galaxy clusters, interconnected by filaments of dark matter, spanning hundreds of millions of light-years across. The significance of superclusters lies not only in their size, but also in what they reveal about the underlying fabric of the universe, the distribution of matter, and the gravitational forces that sculpt the cosmos. Superclusters are crucial for understanding the large-scale structure of the universe. They form at the intersections of cosmic web filaments, the vast networks of dark matter that crisscross the universe, shaping the distribution of galaxies and galaxy clusters. This web-like structure is a direct consequence of the early universe's tiny fluctuations, magnified over billions of years by the gravitational pull of dark matter. By studying superclusters, astronomers can trace the evolution of these structures from the earliest stages of the universe, offering insights into the nature of dark matter and the dynamics of cosmic expansion. One of the most famous superclusters is the Laniakea supercluster, which includes the Milky Way among its tens of thousands of member galaxies. Spanning about 500 million light-years, Laniakea's discovery underscored the interconnectedness of galaxies within the universe, highlighting our own place within these vast cosmic structures. The flows of galaxies towards dense regions within superclusters, driven by gravitational attraction, underscore the dynamic nature of the cosmos, with galaxies constantly moving and interacting within this grand framework. Superclusters also play a pivotal role in cosmology, the study of the universe's origin, structure, evolution, and eventual fate. The distribution and mass of superclusters influence the universe's overall geometry and expansion rate, which are central to understanding cosmological models. Observations of superclusters and their distribution can help refine measurements of the universe's expansion rate, providing evidence for the presence of dark energy, the mysterious force accelerating the expansion of the universe. Moreover, superclusters serve as laboratories for studying galaxy evolution on the largest scales. The environments within superclusters, from the dense centers of galaxy clusters to the more isolated galaxies in their outskirts, offer diverse conditions for star formation, galaxy interactions, and the growth of supermassive black holes. These varying environments help astronomers understand how galaxies change over time and how their evolution is influenced by their surroundings. The cosmic web is a term that captures the breathtaking complexity and vastness of the universe. This web-like network consists of vast strands of galaxies and galaxy clusters, interconnected by bridges of dark matter, enveloping vast voids where few galaxies reside. The cosmic web represents the universe's grandest scale structure, a direct consequence of the uneven distribution of matter following the Big Bang, shaped over billions of years by the gravitational pull of dark matter. Understanding the cosmic web begins with the early universe, moments after the Big Bang, when tiny quantum fluctuations caused slight variations in density across the primordial soup of particles. As the universe expanded, these minute overdensities, magnified by the gravitational attraction of dark matter, became the seeds around which gas and dust could gather and eventually form stars, galaxies, and galaxy clusters. The regions of lower density became the cosmic voids we observe today, vast, empty spaces that punctuate the fabric of the cosmos. The structure of the cosmic web is dominated by dark matter, an invisible substance that constitutes about 27% of the universe's total mass and energy content. Though we cannot see dark matter directly, its presence is inferred from its gravitational effects on visible matter, radiation, and the structure of the universe itself. Dark matter's gravitational pull is what sculpted the cosmic web, drawing matter into the dense regions that became galaxies and galaxy clusters and leaving behind the voids. Galaxy surveys, such as those conducted by the Sloan Digital Sky Survey, SDSS, have mapped the distribution of galaxies across vast stretches of the universe, revealing the intricate patterns of the cosmic web in stunning detail. These surveys show that galaxies are not randomly distributed, but are instead aligned along filaments that span millions of light-years, surrounding great voids and converging at dense, massive nodes where galaxy clusters reside. The cosmic web is not just a static relic of the past, but a dynamic, evolving entity. Galaxies move along the filaments, drawn towards the gravitational wells of massive galaxy clusters. This motion, over cosmic timescales, reflects the ongoing process of structure formation in the universe, driven by the interplay between dark matter and the force of gravity. Studying the cosmic web is crucial for several reasons. It offers insights into the role of dark matter in cosmic evolution, the process of galaxy formation and growth, and the distribution of matter in the universe. Furthermore, understanding the cosmic web helps astronomers to constrain cosmological models, shedding light on the nature of dark energy, the mysterious force driving the accelerated expansion of the universe. Black holes, those mysterious entities at the crossroads of astrophysics and theoretical physics, are integral to the structure and evolution of the universe. These objects, where gravitational pull is so strong that not even light can escape, play a pivotal role in the cosmic ballet, influencing the formation of galaxies, stars, and possibly even the distribution of matter across the cosmic web. The fascination with black holes lies not only in their mysterious nature, but also in their significant impact on the cosmos at large. At the heart of most, if not all, large galaxies, including our own Milky Way, resides a supermassive black hole. These colossal black holes, millions to billions of times the mass of the Sun, are not just remnants of the universe's violent past, but active players in galactic dynamics. They exert a profound influence on their host galaxies, regulating star formation and driving the evolution of galaxies through their energetic outputs. As galaxies merge, so too do their central black holes, releasing vast amounts of energy and potentially shaping the structure of the universe. Black holes also contribute to the cosmic web's architecture by powering quasars and active galactic nuclei, AGN, some of the universe's brightest objects. These luminous beacons, visible across vast cosmic distances, illuminate the intergalactic medium, affecting the formation and evolution of galaxies along the cosmic web's filaments. The feedback mechanisms from AGN, where energy is injected back into the surrounding gas, can halt star formation in galaxies, influencing the large-scale structure of the universe. Furthermore, the gravitational waves produced by merging black holes, detected for the first time in 2015, have opened a new window onto the universe. These ripples in space-time provide a novel way to probe the universe's structure, offering insights into the population of black holes and their role in the cosmic evolution. Gravitational wave astronomy could shed light on the distribution of black holes throughout the cosmic web, further elucidating their contribution to the universe's architecture. The study of black holes also intersects with fundamental questions about the nature of the universe. Theories that attempt to reconcile quantum mechanics and general relativity, such as string theory and loop quantum gravity, often consider black holes as testing grounds for new ideas about space-time, gravity, and the universe's ultimate fate. Black holes are far more than just cosmic oddities. They are central to the structure and dynamics of the universe. From anchoring the galaxies to influencing the cosmic web and offering clues to the fundamental forces of nature, black holes are pivotal in our quest to understand the cosmos. Their study not only challenges our conceptions of space and time, but also highlights the interconnectedness of all cosmic phenomena, from the smallest particles to the largest structures in the universe. On the topic of black holes, let's talk a bit about voids. Voids in space are not just areas of nothingness, but are key to understanding the universe's large-scale structure and its evolutionary history. They are like the negative space in a painting, defining the structure by outlining where galaxies are not, as much as clusters and superclusters tell us where galaxies congregate. The existence of voids supports theories of cosmic inflation and the distribution of dark matter, suggesting that the early universe's quantum fluctuations led to the uneven distribution of matter we observe today. Despite their name, voids are not entirely empty. They contain some galaxies, albeit in much lower numbers than the rest of the universe. These galaxies are often smaller, less massive, and less luminous than those found in denser environments like galaxy clusters. Studying these isolated galaxies can provide insights into galaxy formation and evolution, free from the complex gravitational interactions present in more crowded settings. The discovery and mapping of voids have been made possible by large-scale galaxy surveys, which chart the positions of galaxies across the sky. These surveys reveal the cosmic web's filamentous structure and the vast voids that separate these filaments. The size and shape of voids can vary greatly, with the largest known void in the universe, the Bootes void, stretching approximately 330 million light-years across. These voids are not static, but evolve over time, expanding as the universe itself expands, driven by dark energy's repulsive force. The study of voids also contributes to cosmology, offering a unique vantage point for understanding the universe's expansion and the nature of dark energy. Since voids occupy most of the universe's volume, their dynamics and evolution are essential for a complete picture of cosmic history. Additionally, the distribution and size of voids can be used to test models of the universe, providing constraints on the properties of dark matter and dark energy. The edge of the observable universe, we're venturing into a realm that stretches the limits of our understanding and imagination. This concept refers to the utmost boundary from which light has had enough time to travel to us since the universe's birth, approximately 13.8 billion years ago. It's a horizon that delineates the observable from the unobservable, a cosmic boundary shaped by the age of the universe and the speed of light. The observable universe is a sphere centered around the observer, on Earth in our case, with a radius of about 46.5 billion light-years. This measurement might seem counterintuitive given the universe's age of 13.8 billion years. The discrepancy arises from the expansion of the universe. Space itself has been stretching, carrying light from the early universe far beyond the simple product of its age and the speed of light. Thus, the edge of the observable universe is not a fixed shell, but a dynamic frontier, constantly receding as light from more distant regions reaches us. This edge represents the limit of our cosmic vision, beyond which galaxies and their light have not had enough time to reach Earth. It's important to clarify that this boundary is not an edge in the traditional sense. The universe does not end at this point, but our ability to observe it does. Beyond this frontier lies more of the cosmos, potentially infinite in extent, filled with galaxies, stars, and other cosmic entities we have yet to see. The concept of the observable universe's edge also intertwines with the inflationary model of the early universe, which posits a period of exponential expansion shortly after the Big Bang. This rapid inflation pushed vast portions of the universe beyond our observational reach, contributing to the vastness of the unobservable universe. It's a reminder of the universe's dynamic nature, constantly expanding and evolving over billions of years. The edge of the observable universe is not just a physical boundary, but a temporal one as well. Looking out into the cosmos, we look back in time. The light from the edge of our observable universe brings us information from the universe's infancy, allowing us to witness the formation of the first galaxies and the cosmic microwave background radiation, the afterglow of the Big Bang. These observations are crucial for cosmology, offering insights into the universe's origin, composition, and ultimate fate. At the edge of the observable universe, we find ourselves at the threshold of cosmic discovery and mystery. This boundary, approximately 46.5 billion light-years away from us, represents the farthest we can see into the cosmos and, consequently, the earliest moments of the universe accessible to our instruments. What lies at this frontier is a glimpse into the universe's infancy, a time close to the Big Bang itself, revealed through the oldest light that can reach us, the cosmic microwave background, CMB radiation. The CMB radiation is the afterglow of the Big Bang, the relic radiation left over from the time when the universe was just 380,000 years old and became transparent to electromagnetic radiation. Before this epoch, the universe was a hot, dense plasma of electrons, protons, and photons. Photons, light particles, were constantly absorbed and re-emitted by particles in this plasma, making the universe opaque. As the universe expanded and cooled, protons and electrons combined to form neutral atoms, allowing photons to travel freely. The CMB radiation we detect today is this very light, stretched to microwave wavelengths by the expansion of the universe. Observing the CMB gives us a snapshot of the universe at its earliest, most uniform state, with slight temperature fluctuations that correspond to variations in density. These fluctuations were the seeds of all future structure, the galaxies, stars, and planets that fill the universe today. The study of the CMB has been pivotal in cosmology, providing critical evidence for the Big Bang theory and helping to determine key parameters of the universe, including its age, composition, and rate of expansion. Beyond the CMB and the earliest light, what lies at the edge of the observable universe enters the realm of speculation and theory. The universe beyond our observational reach is thought to continue, possibly infinitely, filled with galaxies, stars, and planets much like the ones we can observe. However, because light from these regions has not yet had time to reach us, their existence remains beyond our current ability to detect or study directly. The concept of the observable universe's edge also challenges our understanding of space and time. In cosmology, the edge of the observable universe is not a physical barrier, but a limit imposed by the speed of light and the age of the universe. As we look further out into space, we also look further back in time. The edge of the observable universe, therefore, represents the earliest moments we can observe and a boundary beyond which the universe remains unknown to us. At the edge of the observable universe lies the ancient light of the cosmic microwave background radiation, a direct link to the universe's birth. Beyond this, the universe likely continues, filled with structures and phenomena yet to be discovered. The expansion of the universe plays a crucial role in shaping what we can see and understand about the cosmos. This expansion, a concept at the heart of modern cosmology, means that the fabric of the universe itself is stretching, causing galaxies to move away from each other over time. This cosmic phenomenon directly impacts our view of the universe, influencing both the observable universe's size and the light that travels across these vast distances. As the universe expands, the light from distant galaxies is stretched along with the space through which it travels. This stretching of light results in a phenomenon known as redshift, where the light shifts to longer, redder wavelengths as it reaches us. The farther away a galaxy is, the more its light has been redshifted, and the faster it appears to be receding from us. This relationship between distance and recessional speed is encapsulated in Hubble's law, named after Edwin Hubble, who first observed this expansion in the 1920s. The expansion of the universe not only affects the light we see, but also limits the portion of the universe that is observable to us. The observable universe is bounded by the cosmic light horizon, the maximum distance from which light has had time to reach us since the universe began. Because of the universe's finite age, about 13.8 billion years, there is a limit to how far we can see. The expansion of the universe stretches this horizon, allowing us to see light from further away. Furthermore, the CMB is a critical tool for determining the universe's fundamental parameters, such as its age, shape, and composition. Measurements of the CMB have helped solidify the understanding that the universe is flat on large scales and have provided precise estimations of the universe's age. They also offer clues about the nature and amount of dark matter and dark energy, two of the most mysterious components of the cosmos that together comprise about 95% of the universe's total mass energy content. The study of the CMB also touches on the very foundations of physics, challenging and refining our understanding of the fundamental forces of nature. For instance, the slight asymmetries and patterns within the CMB have implications for inflation theory, a leading explanation for the universe's rapid expansion just fractions of a second after the Big Bang. This theory predicts a period of exponential growth that would smooth out any irregularities in the universe's density, except for the tiny fluctuations observed in the CMB. Observing the edge of the observable universe presents a series of profound challenges, rooted in both the fundamental limits of our technology and the laws of physics themselves. These challenges encapsulate the vast distances involved, the faintness of the signals we seek, and the complex interplay of cosmic phenomena that can obscure or distort our observations. Firstly, the sheer scale of the universe is a significant obstacle. The edge of the observable universe lies about 46.5 billion light-years away from us, a distance that light has traveled since the universe's inception approximately 13.8 billion years ago, considering its expansion over time. At such vast distances, the light from the earliest stars and galaxies is not only incredibly faint, but also significantly redshifted due to the expansion of the universe. This redshift stretches the light into longer wavelengths, often beyond the visible spectrum into the infrared or even microwave range, necessitating highly sensitive instruments to detect these signals. Furthermore, the cosmic microwave background, CMB radiation, the afterglow of the Big Bang, and the furthest back in electromagnetic radiation we can observe, poses both an opportunity and a challenge. While it provides a wealth of information about the early universe, it also forms a sort of cosmic veil, beyond which traditional observational methods cannot penetrate. This means that any light or other electromagnetic radiation from before this epoch, about 380,000 years after the Big Bang, is obscured from our view. Another challenge in observing the universe's edge involves the limitations of our current technology. While telescopes, both ground-based and in space, have become increasingly sophisticated, there are inherent limits to their resolving power and sensitivity. Observing the faintest, most distant objects requires not just capturing their light, but also resolving it against the cosmic background. Innovations in telescope technology and the development of new observation methods, such as gravitational wave astronomy, offer promising avenues to overcome these hurdles, but they also require substantial time, investment, and technological breakthroughs. Additionally, the interstellar and intergalactic medium, the gas and dust that fills the space between stars and galaxies, can absorb, scatter, and redden light, further complicating observations. These effects can distort the signals we receive, making it challenging to interpret the data accurately without sophisticated models and corrections. Lastly, the theoretical understanding of the universe itself presents a challenge. Our models of cosmic evolution, based on general relativity and quantum mechanics, are tested to their limits at the extreme conditions at the edge of the observable universe. Anomalies or unexpected findings in this region could challenge existing theories, requiring new physics to explain. This intertwining of observation and theory means that understanding the universe's edge is as much a challenge of conceptual innovation as it is of technological advancement. As we dive into the next chapter of this documentary, we encounter something mysterious: dark matter, an enigmatic substance that, despite being invisible and undetectable by conventional means, makes up about 27% of the universe. Unlike the ordinary matter that forms stars, planets, and everything we can see or touch, dark matter does not emit, absorb, or reflect light, making it profoundly difficult to observe directly. Its presence, however, is inferred from its gravitational effects on visible matter, radiation, and the large-scale structure of the universe. The story of dark matter begins with the observation of galaxies and galaxy clusters. In the 1930s, astronomer Fritz Zwicky studied the Coma galaxy cluster and discovered that the visible matter in the galaxies was insufficient to account for the gravitational pull keeping them in the cluster. The galaxies were moving so fast that they should have flown apart if only visible matter were at play. This discrepancy suggested the presence of a significant amount of unseen matter, which Zwicky termed dark matter. Further evidence for dark matter came from observations of galaxy rotation curves by Vera Rubin and others in the 1970s. They found that stars in galaxies rotate faster than expected, based on the gravitational pull of the galaxy's visible matter alone. This again pointed to an unseen mass, providing the gravitational force necessary to hold the galaxies together. Dark matter plays a crucial role in the formation and evolution of cosmic structures. Theories of cosmic evolution suggest that dark matter's gravitational pull was instrumental in pulling ordinary matter into the dense regions that formed galaxies and galaxy clusters. Without dark matter, the universe's structure would be much less complex, and life as we know it might not exist. Despite its pivotal role in the cosmos, dark matter remains one of the greatest mysteries in science. It does not interact with electromagnetic forces, which means it doesn't emit, absorb, or reflect light, making it invisible and detectable only through its gravitational effects. Various experiments are underway to detect dark matter particles directly, including sensitive detectors buried deep underground to shield them from cosmic rays and other background noise. The nature of dark matter is a subject of intense research and speculation. Several candidates have been proposed, including weakly interacting massive particles, WIMPs, axions, and sterile neutrinos, but none have yet been detected. The search for dark matter is not just a quest to understand what it is, but also a journey that challenges our understanding of physics, the universe, and the very nature of matter. In this exploration of dark matter, we confront the limits of our knowledge and technology, embarking on a quest that bridges the worlds of the very large, the cosmos, and the very small, the realm of particle physics. Unraveling the mystery of dark matter is not only about discovering what makes up most of the universe's mass, but also about deepening our understanding of the fundamental laws that govern the cosmos, offering insights into the nature of space, time, and reality itself. Dark matter, while invisible and elusive, leaves a series of cosmic fingerprints that have allowed scientists to deduce its presence and understand its fundamental role in shaping the structure and dynamics of the cosmos. The journey to understanding dark matter's existence began with the observation of galaxy clusters. In the 1930s, astronomer Fritz Zwicky studied the Coma cluster and noticed that the galaxies within it were moving at velocities so high that the visible mass of the galaxies alone could not account for the gravitational force needed to prevent them from escaping the cluster's pull. This discrepancy suggested the presence of a substantial amount of unseen mass, which Zwicky termed dunkel materie, or dark matter. Further evidence for dark matter came from the rotation curves of galaxies. In the 1970s, Vera Rubin and her colleagues measured the speeds at which stars orbit the center of galaxies. According to the laws of gravity, stars on the outskirts of a galaxy should move more slowly than those near the center, where most of the galaxy's visible mass is concentrated. However, observations showed that stars in the outer regions of galaxies were orbiting at the same speed as those closer to the center, implying the presence of a significant amount of unseen mass exerting additional gravitational force. This mass ensures the high orbital speeds at greater distances, a phenomenon that could not be explained by visible matter alone. The cosmic microwave background, CMB radiation, the afterglow of the Big Bang, provides another crucial piece of evidence for dark matter. Detailed measurements of the CMB by satellites such as the Cosmic Background Explorer, COBE, the Wilkinson Microwave Anisotropy Probe, WMAP, and the Planck Space Observatory have shown slight fluctuations in temperature that indicate the early universe's density variations. The distribution and scale of these fluctuations match predictions from models that include dark matter, suggesting that dark matter was instrumental in the formation of the universe's large-scale structure. Gravitational lensing further corroborates the existence of dark matter. This phenomenon occurs when a massive object's gravitational field bends the path of light coming from a more distant object behind it. Observations of gravitational lensing, where the bending of light cannot be accounted for by visible matter alone, indicate the presence of massive invisible structures that can only be attributed to dark matter. Together, these observations from galaxy dynamics, the cosmic microwave background radiation, and gravitational lensing form a compelling body of evidence for dark matter's existence. The role of dark matter in the universe can be likened to the framework of a building, invisible yet essential for holding the structure together. One of its primary roles is in the formation of galaxies and galaxy clusters. In the early universe, dark matter's gravitational pull initiated the coalescence of gas and dust, leading to the formation of stars and galaxies. Without dark matter's gravitational scaffolding, the dispersed gas in the early universe would not have condensed sufficiently to form the stars, planets, and galaxies we observe today. Moreover, dark matter is critical in explaining the rotation curves of galaxies. Observations show that stars at the edges of galaxies rotate at similar speeds to those nearer the center, a phenomenon that defies the expectations based on the visible mass of galaxies alone. Dark matter provides the additional gravitational force needed to explain these uniform rotation speeds, holding galaxies together and preventing them from tearing apart as they spin. At larger scales, dark matter influences the overall structure of the universe, known as the cosmic web. This vast network of galaxies and galaxy clusters, connected by filaments of dark matter and separated by voids, forms the backbone of the cosmos. Dark matter's gravitational effects are responsible for the clustering and distribution of galaxies, shaping them into the intricate patterns observed by astronomers. Without dark matter, the cosmic web's delicate structure, with its filaments and nodes where galaxies cluster, would not exist. Dark matter also plays a vital role in gravitational lensing, a phenomenon where the path of light from a distant galaxy or quasar is bent by the gravity of a foreground mass, such as a galaxy cluster. This effect not only confirms the presence of dark matter, but also allows astronomers to map its distribution in the universe. Gravitational lensing acts as a natural telescope, magnifying and distorting the light from distant objects and providing a unique tool for probing the dark universe. On the topic of dark matter, we find dark energy. The concept of dark energy emerged from observations of distant supernova. In the late 1990s, two independent research teams found that these exploding stars, which serve as cosmic lighthouses, were fainter than expected. This faintness suggested that they were farther away than scientists had predicted, indicating that the universe's expansion rate was not slowing down, as previously thought, but accelerating. This acceleration could only be explained by the presence of an unknown energy component with a repulsive force, overcoming gravity's pull and driving galaxies apart. This component was named dark energy. Dark energy's nature remains one of the most profound mysteries in science. Unlike dark matter, which clusters and helps structure the universe, dark energy appears to have a uniform presence throughout space, exerting the same force everywhere. It does not dilute as the universe expands, a property that distinguishes it from ordinary and dark matter. One leading theory suggests that dark energy might be a property of space itself, described by Albert Einstein's cosmological constant, a term he introduced in his equations of general relativity and later called his biggest blunder. In this view, empty space is not nothing but has its own intrinsic energy. Another possibility is that dark energy is a dynamic field, similar to electromagnetic fields, but with a unique repulsive property. This field, sometimes called quintessence, could change over time, unlike the cosmological constant, which remains constant. Theoretical models propose various forms of quintessence, but as of yet, there is no direct evidence to support these theories. As we delve into the enigmatic nature of dark energy, we uncover its pivotal role in the expansion of the universe, a force that accelerates the cosmos's growth beyond what was once imagined. Dark energy, making up about 68% of the universe's total energy content, acts as a counterbalance to gravity, the force that pulls galaxies and other cosmic structures together. Instead of attracting, dark energy repels, pushing the universe's fabric apart and causing its expansion to accelerate. This acceleration was first observed in the late 1990s through studies of distant supernovae. Astronomers expected these cosmic explosions to show that the universe's expansion was slowing down under gravity's pull. However, the data revealed just the opposite. The universe was expanding faster than in the past, a revelation that pointed directly to the influence of dark energy. Unlike matter, which can cluster and create structures such as galaxies and galaxy clusters, dark energy is evenly distributed throughout the universe, exerting the same repulsive force everywhere, which leads to an increase in the rate of expansion over time. The effects of dark energy on the universe's expansion are profound and far-reaching. As it accelerates the expansion, dark energy influences the ultimate fate of the cosmos. If its strength remains constant or increases over time, the universe could continue expanding indefinitely, growing colder and emptier as galaxies move further apart and star formation eventually ceases. In more extreme models, if dark energy grows stronger, it could lead to a Big Rip scenario, where the repulsive force becomes so dominant that it tears galaxies, stars, planets, and eventually atoms apart. Understanding how dark energy affects the expansion of the universe is not only a matter of measuring the rate of this expansion, but also involves piecing together the history of the cosmos. Observations of the cosmic microwave background radiation, the afterglow of the Big Bang, along with large-scale surveys of galaxies, provide a map of the universe's evolution. These data allow scientists to trace the influence of dark energy back through billions of years, observing how its repulsive force has shaped the cosmos. The study of dark energy and its impact on cosmic expansion is at the forefront of modern cosmology. It challenges our understanding of physics, requiring new theories that can explain its properties and effects. Theories such as quintessence propose that dark energy is not a constant, but a dynamic field that changes over time, which could have varying effects on the expansion of the universe. As we near the end of this chapter on the mysteries of the cosmos, it's crucial to address a common question. Are dark matter and dark energy the same at the edge of the observable universe? Despite their similar names, dark matter and dark energy are fundamentally distinct components of the universe, each playing a unique role in shaping its structure and evolution, even at the very limits of what we can observe. Dark matter, constituting about 27% of the universe's energy content, acts as the cosmic glue that holds galaxies and galaxy clusters together. It exerts a gravitational pull, helping to form the vast web-like structures of galaxies that span the observable universe. Without dark matter, the gravitational forces provided by visible matter alone would be insufficient to prevent galaxies from flying apart due to their rotational speeds. Dark matter's influence is as critical at the edge of the observable universe as it is within our own galactic neighborhood, providing the necessary mass to form the large-scale structures we can detect, even at great distances. On the other hand, dark energy, which makes up about 68% of the universe's energy content, is a repulsive force that drives the accelerated expansion of the universe. Unlike dark matter, dark energy does not clump or cluster, but is thought to be uniformly distributed throughout space. Its effect is to push galaxies away from each other, counteracting the attractive force of gravity. At the edge of the observable universe, dark energy's influence manifests through the observation of the universe's expansion rate, which increases with distance. This accelerated expansion means that the further we look into space, the faster galaxies are moving away from us, a phenomenon directly attributable to the presence of dark energy. The distinction between dark matter and dark energy remains consistent across the cosmos, from our local galactic group to the farthest reaches of the observable universe. Both entities play vital roles in cosmic evolution, but they operate through fundamentally different mechanisms. Dark matter by attracting and dark energy by repelling. This duality underpins the structure and destiny of the universe, influencing everything from the formation of galaxies to the ultimate fate of the cosmos. In exploring the universe's edges, we confront the limits of our understanding, where dark matter and dark energy shape the cosmic landscape in profound yet distinct ways. The ongoing study of these mysterious components challenges our theories of physics and cosmology, driving us toward deeper insights into the nature of the universe. As research progresses, we may find that the roles and properties of dark matter and dark energy evolve with our expanding cosmic horizons, but their fundamental differences remain a cornerstone of our current understanding of the cosmos. Continuing our journey into the cosmic expanse, we embark on an exploration of the various theories we humans have about the universe. Delving into the depths of space and time where the known meets the unknown, this chapter unfolds the tapestry of ideas and hypotheses that stretch our understanding of the cosmos to its limits and beyond. As we proceed, we encounter the bewildering and captivating notion of the multiverse, a theory suggesting that our universe, with its galaxies and stars, might be but a single bubble in a vast cosmic foam of countless other universes. Each of these universes, according to the theory, could harbor different laws of physics, alternate histories, and perhaps variations of reality unimaginable to our human minds. Exploring the concept of the multiverse propels us into one of the most captivating frontiers of cosmology, where the existence of multiple universes beyond our own could redefine the boundaries of reality. This theory, emerging from the confluence of inflationary theory, string theory, and quantum mechanics, suggests a cosmos teeming with an infinite array of universes, each potentially governed by its own set of physical laws and constants. The inflationary theory posits that the universe's rapid expansion just after the Big Bang could have led to the formation of numerous separate space-time pockets, evolving into individual universes within a grand multiverse. Similarly, string theory, in its quest to bridge the gap between general relativity and quantum mechanics, introduces the possibility of numerous dimensions. These dimensions, varying in configuration, hint at a spectrum of universes, each distinct in its fundamental properties. Quantum mechanics adds another layer to this theory with the principle of quantum decoherence, which suggests that every quantum possibility spawns its own universe. This interpretation opens the door to a multiverse where every conceivable outcome is realized in its own parallel universe. Despite the theoretical allure of the multiverse, it remains a speculative frontier, lacking direct evidence. The universes it proposes would exist beyond the observable limits set by the speed of light and the age of our universe, making direct observation or interaction with them a profound challenge. This places the multiverse squarely in the realm of theoretical models and hypotheses, awaiting indirect evidence or innovative theoretical breakthroughs for validation. Physicists and cosmologists are actively seeking signs that could hint at the multiverse's reality, analyzing cosmic microwave background radiation and other cosmic phenomena for potential clues. These efforts push the envelope of our scientific inquiry, testing the limits of what can be observed and understood about the cosmos. Venturing further into the realms of cosmic possibilities and the edges of theoretical physics, we come across the concept of wormholes. Wormholes, often depicted in science fiction as tunnels through space-time, allowing for instantaneous travel across vast cosmic distances or even between different universes, are rooted in real scientific theories and equations. These hypothetical passages through space-time are predicted by the theory of general relativity, which describes gravity as the warping of space-time by mass and energy. The mathematical underpinning for wormholes comes from solutions to the equations of general relativity. One such solution, the Einstein-Rosen bridge, was proposed by Albert Einstein and Nathan Rosen in the 1930s. It describes a tunnel-like structure connecting two separate points in space-time. In theory, a wormhole could connect distant parts of the universe, providing a shortcut that defies the conventional limits imposed by the speed of light. Alternatively, it could link our universe to another, entirely different universe, presenting possibilities that tantalize both scientists and philosophers. However, the existence of wormholes moves beyond their theoretical foundations to the challenge of physical reality and observation. For a wormhole to be traversable and stable, it would require a form of matter or energy with negative density, known as exotic matter, to prevent it from collapsing. Exotic matter would counteract the immense gravitational forces that would naturally close a wormhole, keeping it open for matter to pass through. Yet, exotic matter and the conditions needed to create and sustain a wormhole have not been observed in nature, and their feasibility remains a matter of speculation. The search for evidence of wormholes involves indirect methods, as their direct observation would be extraordinarily challenging. Scientists propose that the gravitational effects of a wormhole on light and nearby matter could potentially be detected with advanced astronomical observations. For instance, a wormhole acting as a gravitational lens, bending the light from a distant star in a manner distinct from known objects like black holes, could provide hints of its presence. Despite the intriguing potential of wormholes, their existence remains purely hypothetical. Theoretical models allow for their possibility, but the laws of physics as we currently understand them and the technological limitations we face put actual wormholes and the prospect of using them for space travel or communication far beyond our reach. The energy scales required to manipulate space-time and create a wormhole, not to mention the exotic matter needed to stabilize it, are well beyond current human capabilities. Continuing on the topic of theories, we find the theory of everything. This ambitious theory seeks to unify all fundamental forces of nature into a single theoretical framework, providing a comprehensive understanding of the physical universe's laws. The quest for the theory of everything represents the pinnacle of human aspiration in physics, aiming to bridge the gap between general relativity, which governs the cosmos's vast scales, and quantum mechanics, which rules the subatomic world. General relativity, Albert Einstein's masterpiece, describes the force of gravity as the curvature of space-time caused by mass and energy. It has passed every test thrown at it on cosmic scales, from the orbit of planets to the bending of light by galaxies. Quantum mechanics, with its principles of uncertainty and superposition, has been equally successful in explaining phenomena at the smallest scales, from the behavior of atoms to the properties of particles in accelerators. Yet, despite their individual successes, general relativity and quantum mechanics remain fundamentally incompatible. General relativity predicts a smooth space-time fabric, while quantum mechanics suggests that space-time at the smallest scales is turbulent and frothy. The theory of everything seeks to reconcile these two pillars of modern physics into a unified framework that can describe all phenomena under a single set of rules. One leading candidate for the theory of everything is string theory, which posits that the universe's fundamental particles are not zero-dimensional points, but rather one-dimensional strings. These strings vibrate at different frequencies, and their vibrations determine the particles' properties, such as mass and charge. String theory is tantalizing because it naturally incorporates quantum mechanics and has the potential to include gravity, suggesting a way to unify all forces. Another approach is loop quantum gravity, which attempts to quantize spacetime itself, treating it as made of tiny loops woven into a fabric. This theory focuses on creating a quantum theory of gravity that is compatible with the principles of quantum mechanics without requiring the extra dimensions or the concept of strings. Continuing on from the theory of everything, we delve into how quantum mechanics itself intricately relates to the cosmos. Quantum mechanics, a fundamental theory in physics that provides a description of the physical properties of nature at the scale of atoms and subatomic particles, might seem at first to be worlds apart from the vastness of the cosmos. Yet, its principles are deeply woven into the fabric of the universe, influencing cosmic evolution and structure in profound ways. At the heart of quantum mechanics are principles such as uncertainty and superposition, which dictate that particles can exist in multiple states simultaneously until observed, challenging our classical notions of reality. These principles don't just apply to the behavior of particles in a lab, they're also crucial to understanding processes that occur on cosmic scales. For example, the nuclear fusion that powers stars, including our Sun, is governed by quantum tunneling, a phenomenon that allows particles to pass through energy barriers. Without this quantum effect, stars would not ignite, and the universe as we know it, teeming with light and life, would not exist. Quantum mechanics also plays a vital role in the early universe. Shortly after the Big Bang, the universe was a hot, dense plasma where quantum fluctuations, tiny variations in energy, occurred. These fluctuations, magnified by cosmic inflation, became the seeds for the large-scale structure of the universe, leading to the formation of galaxies and galaxy clusters. The distribution of matter across the universe, from the cosmic microwave background radiation to the cosmic web of galaxies, bears the imprint of these initial quantum ripples. Furthermore, quantum mechanics is key to understanding black holes, those enigmatic points where gravity is so strong that not even light can escape. Stephen Hawking's work on black holes showed that, due to quantum effects near the event horizon, black holes can emit radiation, known as Hawking radiation. This revelation bridges the gap between quantum mechanics and general relativity, offering insights into how quantum principles apply under extreme gravitational conditions. The intriguing concept of dark matter, which holds galaxies together yet does not emit light, also invites quantum explanations. Several hypothetical particles that could constitute dark matter, such as WIMPs, weakly interacting massive particles, or axions, arise from theories extending the standard model of particle physics, which is grounded in quantum mechanics. The search for these particles involves understanding their quantum properties and how they interact with the gravitational forces shaping the cosmos. On our journey through the realms of quantum mechanics and the cosmos, we naturally progress to a question that has captivated human imagination across cultures and ages. Is time travel theoretically possible? Within the framework of modern physics, the concept of time travel is not merely the stuff of science fiction, but a serious scientific inquiry that intersects with our understanding of the universe's fundamental laws. The theory of relativity, developed by Albert Einstein, provides the most significant theoretical foundation for considering time travel. According to general relativity, the fabric of space-time is curved by mass and energy, and this curvature dictates how objects move through space and time. Remarkably, the equations of general relativity allow for solutions where space-time curves back on itself, forming loops known as closed time-like curves. These structures theoretically permit a path from a point in space-time to the past or future, and then back to the original point, suggesting a possibility for time travel. One hypothetical structure that could allow for such time travel is the wormhole, a bridge or tunnel through space-time that connects distant parts of the universe or different times. If a wormhole could be stabilized with exotic matter, which possesses negative energy density, it might be possible, in theory, to traverse it and achieve time travel. However, the existence of stable wormholes and exotic matter has not been proven, and the practical challenges of creating or finding a wormhole, let alone traveling through one, remain formidable. Another concept related to time travel arises from the idea of cosmic strings, hypothetical defects in space-time left over from the early universe. If two cosmic strings were to pass close to each other, or a single cosmic string were to move in a loop at a significant fraction of the speed of light, they could theoretically create conditions for time travel to the past. Despite these intriguing theoretical possibilities, time travel faces numerous scientific and philosophical challenges. For one, the paradoxes associated with time travel, such as the grandfather paradox, where a time traveler could potentially prevent their own existence, raise questions about causality and the nature of time itself. Moreover, the energy scales required for manipulating space-time to achieve time travel are currently beyond human reach. Quantum mechanics also enters the discussion of time travel, particularly through the concept of quantum entanglement, which suggests a form of communication between particles that is instantaneous and independent of distance. Some interpretations of quantum mechanics propose that entangled particles are connected by wormholes, hinting at a quantum foundation for space-time structures that could, theoretically, allow for time travel. However, leveraging such phenomena for macroscopic time travel remains speculative. Now, let us ask an interesting question. Could life exist elsewhere in the universe? This query not only probes the limits of our understanding of life, but also touches on profound philosophical implications about our place in the cosmos. The universe is vast, with billions of galaxies, each containing billions of stars and potentially even more planets. The Kepler Space Telescope and other missions have discovered thousands of exoplanets, planets orbiting stars beyond our solar system, many of which lie in the habitable zone, where conditions might be right for liquid water, a crucial ingredient for life as we know it, to exist. These discoveries have significantly expanded our understanding of the potential habitats for life, suggesting that the conditions for life could be more common than previously imagined. The search for extraterrestrial life extends from our solar system's planets and moons to distant exoplanets. Mars, with its past evidence of water flow and the discovery of seasonal methane spikes in its atmosphere, has been a primary focus for missions seeking signs of past or present microbial life. Moons like Europa and Enceladus, with their subsurface oceans, offer another tantalizing possibility for hosting life, drawing plans for future missions to explore these icy worlds further. Beyond our solar system, the study of exoplanets has revealed a rich diversity of worlds, including Earth-like planets that could have conditions suitable for life. The characterization of exoplanet atmospheres, though still in its infancy, aims to detect biosignature gases, gases produced by living organisms that could accumulate in a planet's atmosphere, offering a potential indirect method of discovering life. The search for life also delves into the question of what form life might take elsewhere. The life we know is carbon-based, utilizing water as a solvent. However, scientists speculate about the possibility of alternative biochemistries, such as silicon-based life forms or life existing in environments with solvents other than water, like methane or ammonia. This opens the door to a broader understanding of life, potentially existing under conditions vastly different from those on Earth. Continuing our journey through the unknowns of space, our next topic brings us closer to home, exploring the instruments that serve as our windows to the universe, telescopes. These marvels of engineering and science allow us to peer into the vastness of space, from our neighboring planets to galaxies billions of light years away, aiding our quest to understand if life exists beyond Earth and uncovering the mysteries of the cosmos. Telescopes work by collecting and focusing light from celestial objects to create an image. The larger a telescope's light collecting area, the more faint objects it can observe and the more detail it can reveal. There are two primary types of telescopes, refracting and reflecting, each utilizing different mechanisms to gather light. Refracting telescopes use lenses to collect and focus light. The main lens, called the objective, bends incoming light rays to converge at a focal point, where the image is magnified and observed through an eyepiece. Historically significant, refracting telescopes were the first type to be invented, with Galileo Galilei famously using one to make groundbreaking astronomical discoveries in the early 17th century. Reflecting telescopes, on the other hand, employ mirrors instead of lenses. A large curved mirror, known as the primary mirror, reflects light to a focal point. A secondary mirror may then redirect this light to an eyepiece or a camera. Reflecting telescopes have several advantages over refractors, including the elimination of chromatic aberration, a distortion seen in refracting telescopes due to lenses breaking light into different colors, and the ability to construct much larger telescopes since mirrors can be supported from behind, reducing sagging and deformation. Beyond these traditional telescopes, advancements in technology have led to the development of specialized telescopes for observing non-visible forms of electromagnetic radiation, such as radio, infrared, ultraviolet, X-ray, and gamma-ray telescopes. These instruments allow astronomers to explore aspects of the universe invisible to optical telescopes, from the cold dust clouds where new stars are born to the violent high-energy environments around black holes and neutron stars. Radio telescopes, for example, use large dish antennas to detect radio waves from space, providing unique insights into cosmic phenomena like pulsars, quasars, and the cosmic microwave background radiation. Space-based telescopes, such as the Hubble Space Telescope, operate above Earth's atmosphere, which absorbs or scatters much of the electromagnetic spectrum, offering an unobstructed view of the universe in optical, ultraviolet, and near-infrared light. The operation of telescopes, whether ground-based or in space, involves not just the collection of light, but also sophisticated data analysis techniques. Images captured by telescopes are processed and analyzed using computer algorithms, revealing details and structures not visible in raw data. This analysis can include measuring the distance, composition, temperature, and motion of celestial objects, contributing to our understanding of the universe's structure, evolution, and the fundamental laws of physics. Now, let's turn our focus to a monumental leap in our astronomical capabilities: the James Webb Space Telescope, JWST. Launched into space at the end of 2021, the JWST represents the most sophisticated and powerful space telescope ever built, poised to unravel the mysteries of the universe with unprecedented clarity and depth. The JWST is an international collaboration led by NASA, with significant contributions from the European Space Agency, ESA, and the Canadian Space Agency, CSA. It is designed to observe the universe in the infrared spectrum, allowing it to peer through cosmic dust clouds that obscure the view of optical telescopes and to detect the faint light of distant stars and galaxies. With a primary mirror 6.5 meters in diameter, the JWST boasts a light-gathering capacity more than 6 times that of its predecessor, the Hubble Space Telescope, enabling it to observe objects much further away, and therefore much further back in time than ever before. One of the JWST's primary objectives is to explore the edge of the observable universe, seeking to observe the first galaxies that formed after the Big Bang over 13.5 billion years ago. By studying these early galaxies, astronomers hope to learn more about the formation and evolution of the first structures in the universe, shedding light on the processes that led to the complex cosmic web of galaxies we see today. The JWST's infrared capabilities are crucial for this task, as the light from these distant galaxies has been stretched into the infrared range by the expansion of the universe, a phenomenon known as redshift. In addition to exploring the early universe, the JWST will also study the atmospheres of exoplanets, potentially identifying signs of habitability or even life. Its powerful instruments can analyze the chemical composition of exoplanet atmospheres, detecting molecules like water vapor, carbon dioxide, and methane, which could indicate the presence of biological processes. The JWST is also tasked with unraveling the mysteries of star and planet formation within our own galaxy. By observing the molecular clouds where stars are born, the telescope will provide insights into the conditions and processes that lead to the formation of stars and their planetary systems. This knowledge is not only fundamental to understanding our own solar system's origins, but also to comprehending the diversity of planetary systems throughout the galaxy. Building on our exploration of telescopes as humanity's eyes into the cosmos, we turn our focus to a monumental leap in our astronomical capabilities: the James Webb Space Telescope, JWST. Launched into space at the end of 2021, the JWST represents the most sophisticated and powerful space telescope ever built, poised to unravel the mysteries of the universe with unprecedented clarity and depth. The JWST is an international collaboration led by NASA, with significant contributions from the European Space Agency, ESA, and the Canadian Space Agency, CSA. It is designed to observe the universe in the infrared spectrum, allowing it to peer through cosmic dust clouds that obscure the view of optical telescopes, and to detect the faint light of distant stars and galaxies. With a primary mirror 6.5 meters in diameter, the JWST boasts a light-gathering capacity more than 6 times that of its predecessor, the Hubble Space Telescope, enabling it to observe objects much further away, and therefore much further back in time than ever before. One of the JWST's primary objectives is to explore the edge of the observable universe, seeking to observe the first galaxies that formed after the Big Bang over 13.5 billion years ago. By studying these early galaxies, astronomers hope to learn more about the formation and evolution of the first structures in the universe, shedding light on the processes that led to the complex cosmic web of galaxies we see today. The JWST's infrared capabilities are crucial for this task, as the light from these distant galaxies has been stretched into the infrared range by the expansion of the universe, a phenomenon known as redshift. In addition to exploring the early universe, the JWST will also study the atmospheres of exoplanets, potentially identifying signs of habitability or even life. Its powerful instruments can analyze the chemical composition of exoplanet atmospheres, detecting molecules like water vapor, carbon dioxide, and methane, which could indicate the presence of biological processes. The JWST is also tasked with unraveling the mysteries of star and planet formation within our own galaxy. By observing the molecular clouds where stars are born, the telescope will provide insights into the conditions and processes that lead to the formation of stars and their planetary systems. This knowledge is not only fundamental to understanding our own solar system's origins, but also to comprehending the diversity of planetary systems throughout the galaxy. As the JWST begins its mission, it promises to transform our understanding of the universe. Its observations are expected to challenge existing theories, uncover new phenomena, and provide answers to long-standing questions about the nature of the cosmos. From the first light after the Big Bang to the formation of galaxies, stars, and planets, the JWST will offer a window into the universe's history and evolution, bringing us closer than ever to understanding the edge of the universe and our place within it. Over the past few decades, satellites have revolutionized astronomy, providing a vantage point beyond the Earth's atmosphere that is unattainable by ground-based observatories. From the detailed mapping of the cosmic microwave background radiation to the discovery of exoplanets and the monitoring of cosmic phenomena, satellites have opened new windows into the universe, each contributing unique insights that have deepened our cosmic knowledge. The launching of the Hubble Space Telescope in 1990 marked a turning point in space exploration. Orbiting Earth free from the distortions of the atmosphere, Hubble has captured images of unparalleled clarity, revealing the universe's dynamic and detailed structure. Its observations have led to breakthroughs in our understanding of black holes, the age of the universe, the existence of dark energy, and the processes that govern the life cycles of stars. Hubble's deep field images, showing galaxies billions of light years away, have provided a glimpse into the universe's early stages, illustrating the evolution of galaxies over time. Another significant satellite, the Cosmic Background Explorer, COBE, launched in 1989, mapped the cosmic microwave background radiation, the afterglow of the Big Bang. COBE's measurements provided strong evidence for the Big Bang theory, showing the universe's background radiation is remarkably uniform, with slight variations that support models of cosmic inflation. This discovery was pivotal, earning the Nobel Prize in Physics in 2006. Following COBE, the Wilkinson Microwave Anisotropy Probe, WMAP, and later the Planck satellite refined measurements of the cosmic microwave background, producing maps with unprecedented precision. These observations have helped to precisely determine the universe's age, composition, and the rate of its expansion, contributing to the standard model of cosmology that describes the universe as flat and dominated by dark energy and dark matter. Satellites have also been instrumental in the search for exoplanets. The Kepler Space Telescope, launched in 2009, was designed specifically to detect Earth-sized planets in the habitable zone of their stars, where conditions might allow for liquid water. Kepler discovered thousands of exoplanets, revealing that our galaxy is teeming with a diverse array of worlds, many of which challenge our understanding of planet formation and the potential for life beyond Earth. Furthermore, satellites dedicated to observing the Sun, such as the Solar Dynamics Observatory, SDO, have provided detailed knowledge of solar activity, including sunspots, solar flares, and coronal mass ejections. These observations are crucial for understanding the sun's impact on space weather and its influence on Earth's environment. Continuing on the topic, how do scientists use data from telescopes to learn about distant objects? When light or other forms of electromagnetic radiation from distant objects reach a telescope, whether orbiting Earth or stationed on the ground, it is first collected by the telescope's primary mirror or lens. This light is then focused to form an image or directed into instruments like spectrometers, which dissect the light into its component wavelengths. The analysis of this light, across various wavelengths, is fundamental to learning about the properties and behaviors of celestial bodies millions to billions of light-years away. One key method scientists use is spectroscopy, which involves studying the spectrum of light emitted, absorbed, or reflected by objects. Each chemical element leaves a unique fingerprint in the light spectrum, allowing scientists to determine the composition of stars, galaxies, and nebulae. Spectroscopy can reveal not only what distant objects are made of, but also their temperatures, densities, and velocities, towards or away from us, indicated by redshift or blueshift in their spectral lines. Photometry, another essential technique, measures the intensity of light from an object over a range of wavelengths. By analyzing how bright an object appears and how its brightness changes over time, astronomers can infer the object's size, luminosity, distance, and even the presence of planets passing in front of stars. Variations in brightness can also indicate other dynamic processes, such as stars pulsating or binary stars eclipsing each other. The data collected by telescopes often require complex processing and analysis, using sophisticated algorithms and computational models. This process involves correcting for distortions caused by the Earth's atmosphere, instrumental noise, and other sources of interference. The advent of digital imaging and advances in computer technology have dramatically increased the volume and quality of data that can be collected and analyzed, enabling discoveries that were not possible a few decades ago. Astronomers also use the technique of parallax to measure the distance to nearby stars. By observing how a star's position shifts against the background of more distant stars as Earth orbits the Sun, scientists can calculate its distance from us. This fundamental measurement helps in constructing the cosmic distance ladder, which is used to determine the distances of far more remote objects in the universe. As we delve deeper into the cosmos through the lens of powerful telescopes, astronomers confront a myriad of challenges in their quest to observe distant galaxies. These challenges stem from the vast distances involved, the faintness of the objects being observed, and the limitations of our current technology and methods. Overcoming these hurdles is essential for advancing our understanding of the universe's structure, evolution, and the fundamental processes that govern it. One primary challenge is the sheer distance to these distant galaxies, which are millions to billions of light-years away from us. At such distances, the light that reaches Earth is incredibly faint, making these galaxies difficult to detect and study. The expansion of the universe adds to this challenge, as it causes the light from distant galaxies to stretch into longer, redder wavelengths, a phenomenon known as redshift. As a result, much of the light from these galaxies falls outside the visible spectrum and must be observed using infrared and radio telescopes. Atmospheric interference is another significant obstacle for ground-based telescopes. The Earth's atmosphere can distort and absorb the light from distant celestial objects, making them appear blurry and reducing the amount of information that can be gathered. While space telescopes like the Hubble Space Telescope and the forthcoming James Webb Space Telescope are not affected by the atmosphere, they are exceedingly complex and costly to build and launch, limiting the number of such missions that can be undertaken. Additionally, the finite speed of light poses a fundamental limit on our ability to observe the universe in real time. Observing distant galaxies is akin to looking back in time, as we see them as they were millions or billions of years ago, depending on their distance. While this allows astronomers to study the universe's history, it also means that we cannot know the current state of these distant galaxies, complicating our understanding of cosmic evolution. Another challenge is the vast amount of data that modern telescopes generate, which requires sophisticated software and algorithms to process and analyze. Extracting meaningful information from this data, such as the properties of galaxies, the distribution of dark matter, and the rate of cosmic expansion, demands extensive computational resources and advanced techniques in data analysis. Interference from cosmic objects closer to home can also hinder observations of distant galaxies. Light from stars within our own galaxy, as well as interstellar dust, can obscure the view of more distant objects, requiring astronomers to develop methods to filter out this foreground noise and isolate the light from the target galaxies. Despite these challenges, astronomers continue to make significant advances in observing distant galaxies, thanks to technological innovations, the development of more sensitive detectors, and the launch of new telescopes capable of observing the universe in different wavelengths. These efforts are gradually peeling back the layers of the universe, revealing the intricate dance of galaxies across cosmic time and space, and bringing us closer to understanding the cosmos's grandest scales. Entering our next chapter, we journey back in time to the very beginning, the Big Bang. This monumental event marks the origin of the universe as we know it, a singular explosion from which all space, time, matter, and energy emerged around 13.8 billion years ago. Far from being an explosion in space, the Big Bang was the rapid expansion of space itself, setting the stage for the cosmos to evolve from a hot, dense state to the vast, cooler expanse filled with galaxies, stars, planets, and life that we observe today. The Big Bang theory is supported by multiple lines of evidence, making it the leading explanation for the universe's origin. One of the most compelling pieces of evidence is the cosmic microwave background, CMB radiation, a faint glow permeating the universe, discovered accidentally in 1965 by Arno Penzias and Robert Wilson. This discovery provided a direct snapshot of the infant universe, a relic of radiation from about 380,000 years after the Big Bang, when the cosmos cooled enough for photons to travel freely through space. The uniformity and slight variations in the CMB radiation match predictions from the Big Bang theory, offering a window into conditions of the early universe. Another pillar supporting the Big Bang theory is the observation of the universe's expansion. Edwin Hubble's observations in the 1920s of galaxies moving away from each other revealed that the universe is not static, but expanding. This expansion, when traced backward in time, implies that the universe must have originated from a singularly small, dense point. The Big Bang theory explains this expansion and predicts that the farther away a galaxy is, the faster it is receding from us, a relationship known as Hubble's law, which has been confirmed by subsequent observations. The theory also successfully accounts for the abundance of light elements, such as hydrogen, helium, and lithium. Nuclear reactions in the first few minutes after the Big Bang are believed to have produced these elements in proportions that closely match those observed in the universe today. This nucleosynthesis, the process of forming new atomic nuclei from pre-existing matter, provides a crucial test for the Big Bang theory, further cementing its status as the cornerstone of modern cosmology. Despite its success, the Big Bang theory also opens up new questions and mysteries, such as the nature of dark matter and dark energy, which seem to dominate the universe's mass-energy content, and the cause of the universe's initial expansion. Additionally, the theory does not explain what preceded the Big Bang or what triggered it, leaving room for further theoretical developments and discoveries. From the pivotal moment of the Big Bang, the universe embarked on a complex journey of evolution, transitioning from a hot, dense state to the vast, structured cosmos filled with galaxies, stars, and planets we observe today. This evolution is a story of cosmic expansion, cooling, and gravity's relentless work, knitting together the fabric of the universe over billions of years. In the immediate aftermath of the Big Bang, the universe was a seething cauldron of particles and radiation, too hot and dense for atoms to form. During this epoch, known as the Planck era, the four fundamental forces of nature, gravity, electromagnetism, and the strong and weak nuclear forces, were unified. As the universe expanded, it cooled rapidly, allowing these forces to separate and the first subatomic particles, including protons, neutrons, and electrons, to emerge. Approximately 380,000 years after the Big Bang, the universe had cooled enough for electrons to combine with protons and form neutral hydrogen atoms, a process known as recombination. This era marked the universe's transition from opacity to transparency, allowing photons to travel freely for the first time, creating the cosmic microwave background radiation, a snapshot of the infant universe that we can still observe today. For the next several 100 million years, the universe entered the cosmic dark ages, a period before the first stars ignited. During this time, gravity began to pull together the first clouds of gas and dark matter, forming the seeds of future galaxies. The end of the Dark Ages came with the formation of the first stars, whose nuclear furnaces lit up the universe once again. These first generations of stars were massive and short-lived, dying in spectacular supernovae that seeded the cosmos with heavier elements necessary for building planets and life. Galaxies began to take shape, forming from the gravitational collapse of dark matter halos that drew in gas and dust. Inside these galaxies, new generations of stars were born, surrounded by disks of material that coalesced into planets, asteroids, and comets. Over time, galaxies grew through mergers and accretions, creating the diverse range of galactic structures, from spiral to elliptical, that we see today. As the universe continued to expand and cool, the rate of star formation eventually slowed, leading to the current epoch, where the formation of new stars is balanced by the death of old ones. The discovery of dark energy, a mysterious force that is accelerating the expansion of the universe, adds another layer to our understanding of cosmic evolution, suggesting a future in which galaxies become increasingly isolated from one another. Today, the universe is a vast web of galaxies, each a vast island universe of its own, separated by voids and connected by filaments of dark matter. This intricate structure, from the smallest planetary systems to the largest galactic clusters, is the result of nearly 14 billion years of cosmic evolution, a testament to the power of physical laws to shape the universe from the simplicity of the Big Bang to the complex tapestry we observe now. The fate of the universe is a subject of intense scientific inquiry and speculation, intertwined with the laws of physics as we understand them and the critical components that shape cosmic evolution: dark matter, dark energy, and the fundamental forces of nature. The future of the universe largely hinges on the properties and behavior of dark energy, the mysterious force driving the acceleration of the universe's expansion. If dark energy continues to dominate the cosmic landscape, as current observations suggest, the universe will keep expanding at an accelerating rate. In this scenario, galaxies outside our local group will recede from us faster and faster, eventually disappearing beyond the cosmic horizon, rendering them invisible to us due to the finite speed of light. The universe would become increasingly cold and empty, approaching a state known as the Big Freeze or heat death, where it reaches maximum entropy and no significant energy exchanges occur, marking the end of all astronomical processes and potentially the universe itself. Another possibility, though less supported by current observations, is the Big Crunch. If dark energy were to weaken over time, or if the universe contains enough matter to reverse the expansion through gravitational attraction, all matter and space could eventually collapse back into a singularity, possibly leading to another Big Bang and a cyclic universe model. However, the overwhelming evidence for the accelerating expansion of the universe makes the Big Crunch a less likely outcome based on our current understanding. A more speculative outcome is the Big Rip, contingent on a particular form of dark energy that grows stronger over time. In this scenario, the repulsive force of dark energy would become so dominant that it would tear apart galaxies, stars, planets, and eventually atoms themselves, leading to a universe where no structures can exist. In addition to these cosmological scenarios, the future of stars, galaxies, and black holes plays out on vast timescales. Stars will continue to form for trillions of years until the supply of gas in galaxies is depleted. Eventually, existing stars will burn out, leaving behind white dwarfs, neutron stars, and black holes. Galaxies will evolve, merging and cannibalizing smaller galaxies, and their stellar populations will age. Over time, even black holes are expected to evaporate through the process of Hawking radiation, leaving a universe filled with low-energy photons and subatomic particles. These visions of the universe's future are extrapolations based on our best theoretical models and observations. As our understanding of dark energy, dark matter, and the universe's fundamental laws deepens, our predictions may evolve. The study of cosmology remains a dynamic field, where each discovery has the potential to alter our perspective on the universe's past, present, and future. Continuing our cosmic journey, we turn our gaze closer to home, to the fate of our own galaxy, the Milky Way. This majestic spiral galaxy, teeming with stars, planets, and nebulae, is on a trajectory that is both fascinating and inevitable, shaped by the same cosmic forces that govern the universe at large. The Milky Way is currently on a collision course with our nearest galactic neighbor, the Andromeda Galaxy, M31. Astronomical observations and simulations predict that in about 4 billion years, the Milky Way and Andromeda will engage in a titanic merger. This event, far from being a catastrophic collision, will be a gradual process, taking hundreds of millions of years to complete. The vast distances between stars mean that direct star-on-star collisions are unlikely. Instead, the gravitational forces between the two galaxies will warp and reshape them, eventually forming a single larger elliptical galaxy, often referred to as Milkomeda or Milkdromeda. During this galactic merger, the gas and dust clouds in both galaxies will interact, triggering a spectacular burst of new star formation. Some regions will become denser, forming new stellar clusters, while other areas may be stripped away, contributing to the formation of tidal tails, elongated streams of stars and gas pulled from the galaxies. Meanwhile, the supermassive black holes at the center of each galaxy will gradually spiral toward each other, eventually merging to form an even more massive black hole. The fate of the solar system in this cosmic dance is uncertain. The Sun and its planets could be flung into a new region of the resulting galaxy, potentially much farther from the galactic core, or they could remain relatively undisturbed in a similar orbit to their current one. However, by the time the Milky Way and Andromeda merger begins, the Sun will have already entered the final stages of its life cycle, swelling into a red giant and then shedding its outer layers to leave behind a cooling white dwarf. Beyond the Milky Way-Andromeda merger, the long-term fate of Milkomeda will be influenced by the same dark energy driving the universe's expansion. As galaxies outside the local supercluster move away from us more rapidly, Milkomeda will become increasingly isolated in a universe where distant galaxies recede beyond detectable horizons. Over trillions of years, star formation will cease as the available gas is used up or expelled, leaving a galaxy populated by aging stars, white dwarfs, neutron stars, and black holes. In this grand cosmic narrative, the Milky Way's story is a testament to the dynamic and ever-changing nature of the universe. Galaxies are not static islands in the cosmos, but are instead vibrant, evolving entities that merge, form new structures, and give birth to stars and possibly life. Building on the narrative of the Milky Way's eventual merger with the Andromeda Galaxy, let's delve deeper into the cosmic ballet of galaxies colliding and merging, a fundamental process that shapes the universe's structure and evolution. This phenomenon, while it might evoke images of catastrophic collisions, unfolds over vast timescales and distances governed by the inexorable pull of gravity. Galaxy collisions are a natural consequence of gravitational attraction between galaxies that are in close proximity to each other. As galaxies drift through space, their mutual gravitational forces can draw them together. Despite the vast distances between stars within galaxies, when two galaxies begin to interact, it's not the stars that collide, given the immense space between them, but rather the gravitational forces that dramatically alter the galaxy's structures. The initial stage of a galaxy merger involves the interaction of the galaxy's outer halos, composed of dark matter, stars, and gas. These halos exert gravitational forces on each other, causing tidal forces that can distort the galaxy's shapes, pulling out streams of stars and gas. This process can trigger bursts of star formation as gas clouds in the galaxy's spiral arms are compressed. As the galaxies draw closer, their gravitational interaction becomes more intense. The galaxies may pass through each other, their gravitational fields stirring up the internal structures and leading to further bursts of star formation. Over time, the galaxies' mutual gravity slows their relative motion, causing them to oscillate back and forth, gradually losing energy with each pass. During these encounters, the galaxy's supermassive black holes, if present, will begin to influence the merger process. These black holes will eventually sink to the center of the newly forming galaxy, spiraling closer and closer until they merge, releasing vast amounts of energy and potentially producing jets of high-energy particles. The final stage of the merger results in the galaxies coalescing into a single entity. Depending on the original galaxy's masses, sizes, and gas content, the resulting galaxy can take various forms, from elliptical galaxies, which are more rounded and have less gas and dust, to large spiral galaxies if enough angular momentum is preserved. Throughout this process, dark matter plays a crucial role, both in drawing galaxies together and in the dynamics of the merger. The distribution of dark matter around galaxies helps to guide their motion and interaction, influencing the ultimate outcome of the merger. Galaxy mergers are not isolated events, but part of the natural evolution of the universe. They drive the growth of galaxies, influence star formation, and contribute to the complex interplay of processes that shape the cosmic landscape. Observations of colliding and merging galaxies across the universe not only provide spectacular images, but also offer critical insights into the life cycle of galaxies, the behavior of dark matter, and the gravitational forces that orchestrate the cosmos. Journeying into our next chapter, we enter a more philosophical area, pondering a question that bridges science, ethics, and philosophy. Should we try to contact extraterrestrial life? This inquiry taps into the human spirit of exploration and curiosity that has driven us to peer into the night sky, send spacecraft to distant planets, and scan the cosmos for signals of other civilizations. Yet, it also confronts us with profound uncertainties about the nature of extraterrestrial life, and the possible consequences of making contact. The search for extraterrestrial intelligence, SETI, has been an ongoing scientific endeavor for decades, employing radio telescopes to listen for signals that might indicate the presence of intelligent life beyond Earth. Some initiatives have even sent messages into space, aiming to communicate our existence to potential extraterrestrial civilizations. These efforts are grounded in the hope that we are not alone in the universe, and that discovering other forms of intelligent life would be one of humanity's most profound discoveries, offering unparalleled insights into the nature of life, intelligence, and our place in the cosmos. However, the question of whether we should actively try to contact extraterrestrial life is fraught with debate. One argument in favor suggests that making contact could lead to an exchange of knowledge and culture, enriching our understanding of the universe and ourselves. The potential for scientific and technological advancements is immense, possibly offering solutions to challenges we face on Earth, or opening new avenues of inquiry into the laws of physics, biology, and the nature of consciousness. On the other hand, there are significant concerns and risks associated with attempting to contact extraterrestrial civilizations. The history of human exploration and colonization on Earth provides cautionary tales of encounters between civilizations with disparate levels of technology and understanding, often leading to the exploitation or decimation of less technologically advanced societies. The possibility that extraterrestrial civilizations might be far more advanced than us raises questions about their intentions and how they might perceive or interact with us. Furthermore, the diversity of life on Earth suggests that extraterrestrial life forms could be vastly different from us, not only biologically, but in their perceptions, values, and communication methods. These differences raise ethical considerations about the right to initiate contact without a global consensus and the potential impact on humanity and the Earth's biosphere. Philosophical considerations also play a crucial role in this debate. The act of reaching out to the cosmos is a reflection of our desire to understand our existential questions and find our place in the universe. Yet it also requires us to consider the responsibility that comes with such an endeavor, contemplating the implications for not only our species, but any other beings we might encounter. In contemplating whether we should try to contact extraterrestrial life, we are challenged to balance our innate curiosity and quest for knowledge with a thoughtful consideration of the potential risks and ethical dilemmas. This question invites a multidisciplinary dialogue that encompasses not only the scientific and technological aspects, but also the philosophical, ethical, and social dimensions. Diving further into the topic, we find ourselves faced with the profound impact the vastness of the universe has on our philosophical outlook. This immense expanse, filled with billions of galaxies, each home to billions of stars and potentially countless planets, stretches our imagination and challenges our understanding of existence, prompting a re-evaluation of human significance, the nature of life, and our search for meaning. The realization of the universe's vastness brings to light our physical insignificance within the cosmic scale. Earth is but a speck in the galactic neighborhood, which itself is just a tiny fraction of the observable universe. This perspective can evoke a sense of humility, highlighting the fragility and preciousness of life on our planet. It underscores the remarkable coincidence of conditions that have allowed life to flourish here, in stark contrast to the seemingly inhospitable vastness of space. Simultaneously, the universe's enormity and complexity inspire awe and wonder, fueling our innate curiosity and driving scientific and philosophical inquiry. The pursuit of understanding the cosmos serves as a testament to the human spirit's resilience and our relentless quest for knowledge. It challenges us to push the boundaries of our cognitive and technological capabilities, seeking not only to uncover the mysteries of the universe, but also to explore the depths of human consciousness and the limits of reason. The possibility of other life forms, perhaps on countless worlds scattered across distant galaxies, invites us to ponder the universality of experiences such as consciousness, morality, and the search for meaning. It raises questions about the potential for communication and understanding between vastly different forms of life, and the implications for concepts of morality, rights, and the interconnectedness of all beings. The discovery of extraterrestrial life would not only revolutionize our scientific understanding, but also fundamentally alter our philosophical and ethical frameworks, challenging anthropocentric views and expanding our conception of the community of life. On a more existential level, the vastness of the universe confronts us with the temporal and spatial limits of our existence. It forces us to grapple with questions about the beginning and end of the universe, the nature of time, and our place within this grand continuum. The realization that the universe has existed for billions of years before us and will continue long after we are gone can evoke a search for meaning and purpose that transcends individual lives, leading to reflections on legacy, memory, and the impact of our actions on future generations and the cosmos itself. So, how do we balance the cost of space exploration with Earth's needs? This question strikes at the heart of our ambitions to venture beyond our planet, challenging us to weigh the boundless potential of cosmic discovery against the immediate and tangible demands of our home world. It encapsulates a broader debate about resource allocation, societal priorities, and the long-term vision for humanity's future. Space exploration, from sending humans to the Moon and Mars to launching telescopes that peer into the universe's farthest reaches, requires significant financial investment, technological resources, and human capital. The endeavors to understand the cosmos, search for extraterrestrial life, and possibly colonize other planets inspire awe and push the boundaries of human potential. They yield technological advancements, scientific breakthroughs, and a deeper understanding of our place in the universe, benefits that can ripple through society in unexpected and transformative ways. However, Earth faces pressing challenges, including climate change, poverty, disease, and resource scarcity that demand immediate attention and resources. The juxtaposition of investing in space exploration, while these urgent issues persist on Earth, raises ethical and practical considerations. It prompts a critical examination of how we prioritize funding and resources, ensuring that our pursuit of the stars does not overshadow our responsibilities to our planet and its inhabitants. Balancing these seemingly competing interests requires a nuanced and forward-looking approach. It involves recognizing that investments in space exploration and addressing Earth's challenges are not mutually exclusive, but can be complementary. Technological innovations developed for space missions, such as satellite communications, GPS technology, and advances in materials science, have found critical applications on Earth, improving environmental monitoring, disaster response, and everyday conveniences. Moreover, exploring space can contribute to solving Earth's challenges. Studying other planets, particularly Mars and Venus, offers insights into climate change and environmental degradation, providing valuable lessons for managing Earth's ecosystems. The search for extraterrestrial life emphasizes the uniqueness and fragility of our biosphere, highlighting the importance of preserving Earth's biodiversity. A sustainable approach to space exploration also involves international cooperation, sharing the financial burden and the rewards of discovery among nations. Collaborative space missions can unite humanity in a common purpose, transcending geopolitical boundaries and fostering a global community that values both exploration and stewardship of our home planet. Furthermore, engaging the public and fostering a culture that values science, education, and exploration can generate widespread support for space missions while encouraging responsible management of Earth's resources. Public and private partnerships in space endeavors can also alleviate financial pressures on governments, allowing for innovative funding models that support both space exploration and Earth's sustainability. Entering our last chapter of this documentary, we look into the future, our own future, and delve into one of the most captivating quests of modern science. How close are we to discovering life on other planets? This question lies at the intersection of numerous scientific disciplines, including astronomy, biology, and planetary science, and it resonates deeply with our innate curiosity about whether we are alone in the universe. The search for extraterrestrial life has taken significant strides in recent decades, propelled by remarkable advancements in technology and a better understanding of where to look for signs of life. At the heart of this quest are exoplanets, planets orbiting stars outside our solar system, some of which lie in the habitable zone, the range of distances from a star where liquid water could exist on a planet's surface. Thanks to missions like NASA's Kepler Space Telescope and the Transiting Exoplanet Survey Satellite, TESS, we have identified thousands of exoplanets, a small but promising number of which are Earth-sized and within their star's habitable zone. These discoveries provide a catalogue of worlds where life as we know it has the best chance to thrive. The upcoming James Webb Space Telescope, JWST, is set to revolutionize our search for life beyond Earth. With its unparalleled sensitivity to infrared light, JWST will be able to study the atmospheres of exoplanets in detail, searching for chemical signatures of life, such as oxygen, methane, and water vapor. These molecules, particularly when found together, could indicate biological processes at work. Meanwhile, missions within our solar system offer another pathway to finding life. Mars, with its past evidence of water, is a prime candidate, and both NASA's Perseverance rover and the European Space Agency's ExoMars rover are equipped to search for signs of past or present life. Additionally, the icy moons of Jupiter, Europa, and Saturn, Enceladus and Titan, harbor subsurface oceans that could provide environments suitable for life, and missions like Europa Clipper and the proposed Enceladus Life Finder aim to explore these alien seas. Despite these advancements, the discovery of life beyond Earth remains elusive. The primary challenge lies in the vast distances that separate us from potential habitable worlds, making direct exploration a distant possibility. Furthermore, our search is constrained by our understanding of life, which is based solely on Earth's biology. Life on other planets could take forms that are entirely unfamiliar, requiring us to broaden our definitions and methods of detection. As we contemplate the future of our cosmic journey and the tantalizing possibility of discovering life on other planets, our path is inextricably linked to technological advancements. These advancements will not only refine our current capabilities, but also unlock new realms of exploration and understanding. The quest to further explore the universe calls for innovation across multiple domains, from propulsion systems that could carry us to distant worlds, to instruments that can unveil the secrets of the cosmos with unprecedented clarity. One critical area of development is in propulsion technology. Current spacecraft propulsion methods are limited by the speed they can achieve, making interstellar travel impractical within human lifetimes. Concepts such as ion drives, nuclear thermal propulsion, and even theoretical ideas like antimatter engines and warp drives represent the cutting edge of research that could one day enable us to reach other star systems. Furthermore, the potential of light sail technology, propelled by laser beams to achieve significant fractions of the speed of light, offers a tantalizing glimpse into a future where interstellar probes could be sent to nearby star systems. Another vital technological frontier is in telescope and observation technology. The James Webb Space Telescope represents a monumental step forward, but the future holds even greater promise. Extremely large telescopes, both in space and on Earth, equipped with advanced adaptive optics to correct for atmospheric distortions, will be able to image exoplanets directly, possibly capturing surface details. Additionally, the development of more sensitive detectors and the use of interferometry, where light collected by multiple telescopes is combined to improve resolution, could allow us to study the chemical composition of distant planets' atmospheres in search of biosignatures. Robotics and automation will also play a crucial role in the future of space exploration. As missions venture farther into the solar system and beyond, the need for autonomous spacecraft capable of making decisions in real time without waiting for instructions from Earth becomes increasingly important. Advances in artificial intelligence and machine learning will enhance the autonomy of probes and rovers, enabling them to navigate challenging terrains, conduct scientific experiments, and adapt to unforeseen conditions. Moreover, the miniaturization of technology and the development of CubeSats and nanosatellites open new possibilities for space exploration. These small, cost-effective platforms can be deployed in large numbers to study cosmic phenomena, monitor asteroids, and even serve as communication relays for interplanetary missions. Lastly, the sustainability of space exploration necessitates advancements in life support and habitat technology. Long-duration missions to Mars and beyond will require closed-loop life support systems that recycle air, water, and waste, as well as advanced habitats that protect astronauts from cosmic radiation and extreme temperatures. The development of in-situ resource utilization, ISRU techniques, which involve extracting and using resources from the Martian soil or asteroids, will be crucial for building sustainable off-Earth colonies. A question that resonates with both scientific curiosity and profound philosophical implications is what message we, as humanity, would choose to send to an extraterrestrial civilization. This question not only contemplates the practical aspects of interstellar communication, but also reflects on the essence of our identity, our achievements, and our aspirations as a species. Crafting a message to extraterrestrial beings is an exercise in distilling the vast and varied experiences of human existence into a form that can be understood across the cosmic expanse. It requires us to consider what aspects of our world we wish to share and what universal truths we might convey. The content of such a message would need to bridge the chasm of not only interstellar space, but potentially vast differences in perception, cognition, and culture. A foundational element of our message could be the language of mathematics and the physical laws that govern the universe, as these are likely to be universal constants. Descriptions of fundamental mathematical concepts, the structure of the atom, and the principles of light and energy could serve as a common ground for establishing communication. Visual representations of these concepts, alongside binary sequences or other forms of universal coding, could provide a basis for mutual understanding. Beyond the scientific, the message would ideally reflect the diversity and richness of life on Earth. This could include images or descriptions of our planet's biosphere, from the microscopic world of cells and DNA to the vast landscapes and oceans, and the multitude of life forms that inhabit them. Such a portrayal would offer a glimpse into the complexity and beauty of life as it has evolved on our world. Music and art, as expressions of human creativity and emotion, could serve as ambassadors of our cultural heritage. Selected pieces that evoke a range of emotions and ideas might transcend the boundaries of language and offer a sense of the human spirit. Similarly, greetings in multiple languages, along with expressions of peace and a desire for friendship, could convey our social nature and our hope for a peaceful exchange. Philosophical and ethical principles that guide human societies, along with our aspirations for the future, would also form a crucial part of our message. This could involve our quest for knowledge, our dreams of exploration and understanding, and our commitment to the stewardship of our planet and the life it sustains. In contemplating the message to an extraterrestrial civilization, we are also reflecting on ourselves, on the values that define us, and on the legacy we wish to share with the cosmos. It is a declaration of our existence, a testament to our journey through time and space, and an invitation to connect across the vast, starry expanse. As we end our journey through the cosmos, from the fiery birth of the universe in the Big Bang to the unknowns beyond our universe, we find ourselves at a profound crossroads of knowledge and imagination. This voyage has not only illuminated the depths of space and time, but also cast a reflective light on our own existence, our planet, and the shared destiny that binds us to the cosmos. Through our telescopes, satellites, and probes, we've begun to unravel the universe's grand narrative, discovering the fundamental laws that govern its expanse and the myriad phenomena that populate it. We've glimpsed the potential for life beyond Earth, sparking questions about our uniqueness and the possibility of communication with other intelligent beings. The technological leaps envisioned for the future promise to deepen our understanding and expand our reach into the galaxy, perhaps even beyond. Yet, with each discovery, new questions arise. The universe, with its dark matter and dark energy, its billions of galaxies and potential multiverses, remains a vast, mostly uncharted territory that challenges our deepest scientific and philosophical inquiries. The possibility of life elsewhere redefines our search for meaning and our place within the cosmic tapestry. As we end our journey, we are left with a sense of awe for the universe's vastness and a hopeful gaze toward the future, pondering the next chapter in the human story, a chapter not yet written, filled with mystery and adventure. What do you think is outside our universe? Subscribe and comment your thoughts below. Thanks for watching.